Chapter 2 is an introduction to functions. So this Venn diagram represents that all functions are relations. So relations are just sets of ordered pairs, x and y. But a function is a special relationship in which for each x there's one unique y. That's why we did the vertical line test. So the vertical line test means that if you draw an imaginary vertical line through every single part of the graph, it's only going to cross an x once. So this would be, yes, this is a function. Whereas if I had a graph like a sideways parabola, this would not be a function because it would cross, the x would have two different y values. This is not a function. So there's a few different function relationships we have studied in this chapter. The first one that we started with was a linear function, which you might remember, or that you will remember from algebra. And we talked about the three different forms: standard form, point-slope form, slope-intercept form. And then we also moved into direct variation. So linear functions can take the shape of many different forms. So there's slope-intercept, there's point-slope form, and there was standard form where a is positive and a, b, and c are integers. And so direct variation is a special type of linear function. So direct variation looked like y equals kx, where k was the constant of variation. We talked about how direct variation was a special type of line, a constant increase or decrease situation such that it passed through the origin. Whereas a linear function does not have to have a y-intercept of 0. Direct variation is very specific in that the y-intercept is 0. So that's kind of how you can tell if a linear function is a direct variation function. Then we also talked about absolute value functions. It takes on the form y equals a times x minus h plus k, where the translation of the function is the h and the k. So the h and the k is the vertex when it's in this form. This a value right here tells you if the function has been reflected across the x-axis or not. So if a is positive, then that means it opens up. But if a is negative, it means it's been reflected over the x-axis and it opens down. We also talked about how a has a stretch or a shrink aspect to it. So we talked about if we took the absolute value of a and it was between 0 and 1, then it was going to be a vertical shrink. This is shrinking in the vertical direction. This was a vertical shrink. Vertical. But we also talked about if the absolute value of a was greater than 1, it was going to be a vertical stretch. It's getting narrower. It's increasing faster. I shouldn't say it's increasing faster. So this would be like a slope of 3, whereas this one would be a slope of 1/3, 1/3. So this one is rising as x goes over 1, it's rising more. Okay, then at the end of the unit we talked about linear inequalities. So if you remember, then inequalities could be at least, more than, no less than, no greater than. So you should read that those are the keywords that we're talking about inequalities. So inequalities are less than, greater than are going to have a dashed line, and less than or equal to and greater than or equal to are going to have a solid line. So when you're solving for linear inequalities and you're graphing, you just need to be careful that you solve for y, because you might have, like in this case, you're going to have to divide by negative, and you're going to eventually flip the sense of the inequality. So I would just suggest that you solve for y when graphing it. Absolute value inequalities might have been something new. So if you have to graph a function such as this, what would you do first is start at the vertex. So the vertex is at -5, -6. So I make a dot here. I know that my a is positive, I'm opening up, and the slope is 1. So at the end, I should be going over here too. So at the end you have to look at this right here. Tells me it's going to be a dashed line. So I make a dashed, and then I'm shading less than, so I shade underneath the function. So don't forget your shading, don't forget about the boundary line and the shading. So just to recap, direct variation is of the equation is going to be y equals kx. It's going to be y equals the number k times x. This k is the constant, which is just a number. So to get the k, you need to do y divided by x. And then absolute value functions take the form of a times x minus h plus k. It can also be, you can have different absolute value functions too that we looked at that you could make with a t-table. But the generic absolute value is just going to be y equals a times x minus h plus k. The vertex of this is at hk, and we also talked about the transformations that a function can go through, and we use the acronym RTV. Whereas R, what type of reflection do we have? We're reflecting over the x-axis when this is negative. And we talked about translation. So translation means, how are we shifting? Are we shifting up, down, left, right? What are we doing? So we want to be specific on how we're shifting. Just don't write up and downs. You want to be specific. Up 2 units, left 3 units, that's our translation. And we also did the vertical stretch and a shrink. That is from the a value right there. So let's do an example. So if I had y equals 2 times x minus 1 plus 4. If I'm going to describe this transformation, I'm going to think of the R, T, V. So is it reflected about the x-axis? No, because the number in front of the absolute value is positive. So it's not being reflected across the x-axis. The T stands for translation. So how has this been shifted? Up, down, left, or right? So you want to be specific. This x minus 1 means it's going to go right 1, and this plus 4 means it's going to go up 4 units. And the V is vertical stretch or shrink. So because the value in front of here is not equal to 1, it's either a vertical stretch or a shrink. Since this number is 2, it's a vertical stretch of a factor of 2. So if I'm going to use this, what I'm going to do is I'm going to graph this. I'm going to start at the vertex, and I'm going to go right 1, up 4, make a dot, and it's going to open up because this is positive. So up 2 over 1, up 2, left 1, and it looks like this. If I were to discuss the x-intercept, the y-intercept, there are no x-intercepts. It does not cross the x-axis. But the y-intercept is at 6, so I think you should write it as an ordered pair. 0, 6 is the y-intercept. And there are no x-intercepts. And we also talked about linear regression. So linear regression was if you had data that was closely resembling a line. So you could actually draw a pretty decent line with this data. If we do it by hand, we're going to get many different answers if we're not being exact enough, if we're not having good graph paper, and if we have decimal numbers. So we can use it in our calculator. So to do it in your calculator, remember we used the button Stat, then we went to Edit, and we put numbers into our L1 and L2. So L1 were our X values, and then L2 was our Y values. After we inputted those values in, we went to Stat, then we went to Calc, and we did linear regression. So we hold this, I want you to hold this function in your calculator by then going into your y equals screen, hitting the variables button, then we slid down to the statistics button, then we went over to the EQ button, which is equation, and then we did the regression equation. This will store this into your y equals when you have so many different variables. So this should say regression equation. And the video of that too is on the website. Okay, so linear functions, make sure you know how to find, these are just the basics of linear functions. Make sure you know the slope formula. Make sure you can go in between among these three right here, standard form. And don't forget to find the x and the y-intercept. So the x-intercept of a linear function is where it crosses the x-axis. Therefore, you set y equal to 0 and solve for x, and the y-intercept is where it crosses the y-axis and you set x equal to 0 and solve for y.